I'm delighted to be here speaking to you this morning, and I'm especially delighted that it's the first slot, because I just flew in yesterday afternoon, so by later on today, I may not be quite as coherent once the jet lag really kicks in. At the moment, I'm full of coffee, so it's all good. So a little about me. I've been a developer, an architect. I spent some time in operations. From my time in operations, I expected I'd spend my time replacing failed hard drives and CPU fans and whatnot. What I actually spent my time doing was restarting failed applications. And so from that, I learned that our software wasn't surviving production all that well. And I wrote this book called Release It. I'm pleased to say it was embraced by the community, so much so that my editors came back and said, you know, a few things have changed since 2007. I'm like, oh yeah, there was that cloud thing. So they convinced me to write this second edition. It's about 3/4 new. That came out early last year, available in all the usual places. Beyond that, this is actually my second trip to Krakow just this year. I was here earlier in June because this year I joined a company called Sabre, which has a pretty large development center here in Krakow. And so I've been coming over to work with my colleagues here, and I'll actually be doing that for the balance of this week. We are hiring. We are reimagining the business of travel, and I'm working with a group here that's doing a bunch of Kubernetes work and platform services to get us off of that old mainframe and into kind of a new world. Is this my adapter causing the blinking, or is it something else? This may be distracting. So I want to talk about a situation that maybe a lot of you have experienced. Certainly I have. It's when you believe you've got a pretty good system running. You've spent time refactoring it. It's been in production. You've been working with it. It's a nice, habitable environment. You might even say it's elegant or beautiful. Things are going well until that fateful day when someone asks for a change. And that change doesn't seem to be all that easy to implement. You start adapting one area for a requirement, and something very far away in the structure breaks. And it's not exactly clear why. So following the advice, you refactor your system until it's easier to implement the change. And as you go, you discover that things are showing action at a distance. What you realize is you don't have this beautiful crystalline structure that you had in your head. You have something more like a tensegrity structure. This was a style of architecture that Buckminster Fuller was popularizing in the 1960s, where everything was made out of beams and cables. Beams are pretty good at compression. You can't compress a cable at all, but they're pretty good under tension, and beams are terrible under tension. So you've got these two different parts that complement each other, and it turns out you can build these weird, airy structures out of this that don't look like they should hold together at all, but they're actually very, very stable until you remove the one critical beam, and then it all falls apart. And as you continue pushing on your system, it feels like the system is pushing back. And you realize you don't even have tensegrity, you kind of have no-tegrity, and you're gradually being absorbed by the chaos of this system. A rewrite starts to sound pretty good at this point. Greenfield development, how hard can it be? It's only 2 weeks, right? When people start to ask, you know, what happened? Why are we blowing the estimate by a factor of 3? You say, well, the systems were much more tightly coupled than we thought they were. We need to talk about coupling, because in our industry, when we say coupling, it's a dirty word. It's a bad thing. We talk about things should be as loosely coupled as possible, but actually, in a lot of other industries and areas, coupling is not a bad word. In fact, coupling can mean safety. So as we dissolve our large systems into pieces, this notion of coupling becomes even more important. And I want to examine some of the places where coupling means structure rather than resistance. So for example, this is a Scharfenberg coupler. This component at the front of the train holds two train cars together. It's a clever arrangement of rods, springs, and discs, such that as you bring the cars together, there's an increasing amount of resistance until you reach a critical point. A cam turns around a certain distance, a rod slips into a gap in the cam, and now the two cars are very tightly held together, and they won't come apart unless you insert a key into the side and deliberately uncouple these train cars. Now, this is one of the reasons that train cars coming apart are not nearly as much of a problem in modern days as cartoons led me to believe when I was a kid. Although I did find out that for a time in Britain, they would actually drop people off at various stations by just unhooking the last couple of cars of the train. So the engine would continue on, and the last couple of cars would drift to a stop somewhere in the vicinity of the depot. So that was interesting. This coupler has been around for more than 100 years, still used today. Here's another kind of coupling called Watt's linkage. Watt's linkage allows you to turn rotary motion into an approximation of linear motion. And you can see across this sort of S-shaped area in the center, there's a pretty broad range where the point P more or less describes a line. This was invented by James Watt, and it allowed them to use coal boilers to turn shafts to pump water out of coal mines, to dig up more coal, to run the coal boilers to pump water out of coal mines. Now, I'm sure there was another purpose for it somewhere along the way, but that was the major reason that they built this thing. And I want you to notice it's a very small number of parts. It's 3 beams and 4 couplers. Here's another linkage, a Chebyshev linkage, also made of 3 beams and 4 couplers. It describes a better approximation of linear motion, but the really interesting thing here is it's the same parts, just arranged in a different way to produce different behavior. The key part, or key components in all of this are the couplers at those pivot points. I'm somewhat of an aficionado of physics. And in physics, we have something called the Standard Model, which describes the fundamental particles that make up the universe. And the Standard Model is sometimes shown in this graph form where the lines indicate coupling coefficients. Every one of those lines has a number attached to it that indicates how strongly one field couples to another field. If there were no coupling, nothing would exist. No coupling means that the two fields don't interact, and so you can't have mass or energy, or matter. So coupling is kind of an important thing in these other areas. We have coupling and couplers in closer, more familiar structures as well. For instance, your knee is a coupler. It allows motion in a certain plane, so it determines 1 degree of freedom. You can swing your knee back and forth, but it doesn't go side to side. So it enables that kicking motion. It inhibits motion perpendicular to that plane. And it allows you to connect effects. Muscles in one part of your leg affect another part of your leg. There's always somebody who points out that your knee can, in fact, bend in other ways. And I point out, yes, it can, but only once. When we talk about coupling effects, I found a particularly beautiful and cosmic arrangement of coupling. This is a moon of Saturn called Iapetus. It's sometimes called the Death Star moon because of this rather prominent crater down here. A little less visible is that it's got an equatorial ridge that makes it look a little bit like a walnut. But certainly the most prominent thing you observe is this coloration. These colors are not really adjusted. One side really is significantly darker than the other side. And for a long time, nobody knew why. This moon was originally discovered by Giovanni Cassini. He was a contemporary of Galileo, and he was the one who discovered that Saturn had rings and moons. Well, in 2009, we finally discovered the likely cause, and it's this. A tiny little moon of Saturn called Phoebe. Astronomers have this criterion for bodies. If they are big enough to pull themselves into a sphere under gravity, they're considered sort of legitimate. So astronomers would sneer at this a little bit. Look at that moon. It's so dinky, it's not even a sphere. In fact, it's so small, it's about 213 kilometers across. You could play golf on this moon and knock a ball not only into orbit, but at escape velocity, so it would eventually hit Saturn. And in fact, this happens with pretty high frequency. And not people playing golf, but things getting blown off of this moon by micrometeoroids. They eject dust and material from this moon, which becomes this outermost, very faint ring of Saturn. At the outer edge of this ring is Phoebe. At the inner edge is Iapetus. So material gets blown off of Phoebe, orbits Saturn for millions of years, is affected by solar pressure. So sunlight has pressure, and when you're on the side closer to the sun, you get more pressure. When you're farther away, you get less. This causes the material to spiral inward where it's swept up by Iapetus, which is tidally locked, so it's always showing the same face forward. So think about the coupling we have involved here. We have gravity, we have sunlight, we have tides, and millions of years. Coupling really is everywhere. And the more you look for it, the more you realize everything is coupled to everything else. All of the systems we build sit in a gravitational well. All of them are exposed to temperature. If you've worked in data centers, you're probably pretty aware of the ambient temperature issue. But you probably don't think about acoustics. All of them sit inside air, and so they can get vibrations. Turns out, acoustics sometimes matter. There's a great video on YouTube of a guy I know screaming at hard drives and watching the failure rate go up. So you can actually see increased latency and increased read failures from vibrations on disks. Well, it's kind of funny when he's sitting there screaming at them, but if you think about vibration being caused by, fans and power supplies and vibrations being transmitted through the floor up into racks, into drives, you start to realize maybe this matters. Now, I don't know about you, but I don't tend to write my software to be aware of acoustic vibrations in the hard drives. Some of these things matter more at some times, and other things matter less. We can't pay attention to all of the things all of the time, or we'd never get any work done. So the more I was contemplating coupling, the more I started to think we need some way to analyze the coupling that we're dealing with. And I found that there are different kinds of coupling. And these different kinds of coupling inhibit different kinds of changes. We'll be talking about these as I continue through this session. Operational coupling is the one that's most visible when something goes down in production. So operational coupling means the consumer can't run if the provider is not available at that time. This was a kind of coupling we didn't worry about much in the monolith days or when we were writing single programs, but in distributed systems we have to worry about it a lot. Development coupling is the kind when we have to make corresponding changes on both ends of an interface. If you've ever had to deploy two applications at the same time because you've changed the interface on both sides, you've experienced development coupling. It's possible for something to have development coupling and not operational coupling, and vice versa. Semantic coupling is a little less obvious, so we'll explore it some more, but it occurs when you have the same concept represented in multiple places, and a change in the concept requires a change in different places. This might not be systems that call each other directly, but they may be systems that are representing the same business idea or the same technical concept. Functional coupling is sort of the inverse. You're not necessarily dealing with the same concept, but you're dealing with similar implementation. So if you've had to do a widespread upgrade of your messaging technology because you're updating your middleware, then you've experienced some functional coupling. And then, of course, there's incidental coupling where there's just no damn reason that these things should have to change together, but they do. I had an application server that wouldn't start up unless the IBM MQ broker was running. It could run just fine without the broker being there, but the broker had to be there at startup in order to boot cleanly. Incidental coupling. Now, any of these can be latent or it can be explicit. You should always prefer explicit coupling over latent coupling. At least with explicit coupling, you have some chance of searching your code or searching your documentation to find out about it. I want to get a little bit of practice working with this framework and understanding these types of coupling. So here we have an interface between a component, in this case it's a C# component running inside some service, and it's sending a notification via Microsoft Exchange. So it sends this email out. When we think about the operational coupling, we say, could this email component function if Exchange is not there? No. There's nothing to send. SMTP is synchronous, it's connection-oriented, it's conversational. If you interrupt it, you have to restart. So very strong operational coupling. The development coupling, on the other hand, is weak. What are the odds that you make a change to your email component that motivates Microsoft to release a new version of Exchange? Pretty low odds. It might go the other way around. But SMTP has been around for a long time, so generally speaking, those kinds of issues have been sort of driven out of the protocol. So we normally don't have that development coupling. What about semantic coupling here? It turns out the semantic coupling is very strong. Your email sending component needs to understand the entities and the attributes that are defined by the Exchange server. So the notion of an email message, of recipients, of attachments, maybe even the MIME encoding, all of that has to be shared between both sides. So we have a strong semantic coupling. If we said, instead of sending email, we now need to write a PDF into a directory, we would reasonably expect a high degree of change in this email component because it's no longer going to be an email component. In terms of functional coupling, we probably don't have very much. Remember, functional coupling is when you share implementation technology. So it's certainly possible that you have linked in some DLL that Exchange provides, but not terribly likely. You could write this email component in many other languages, many other frameworks that wouldn't need that. So the functional coupling is pretty weak. All right, we're going to look at another case now where we try to gradually evolve away from a certain type of coupling. So we have here a different pair of components. Now we have something that is importing reference data from some other reference data system. And we're going to suppose for the moment that that reference data system exposes a database directly. And you're doing that thing that nobody likes to do now, which is reach into another system's database and query it. Well, in terms of the operational coupling, it's quite strong. If the database is not available, I can't import any data from it. The development coupling, probably also quite strong. So changes to the schema over there that would cause a release of the reference data system are very, very likely to cause changes over here in my consumer. Semantic coupling, also quite strong. I'm using SQL, so I know that I'm talking to a relational database. I know that I've got entities. I probably even have classes over here representing concepts like table, column, query, insert, and so on. The functional coupling can be weak. Can be, doesn't need to be. I certainly do need to know how to talk the right protocol to get to that database, but beyond that, the functions of a database server and a client aren't all that similar, so it's unlikely that we have a lot of shared implementation. So we look at this and we say, that very strong operational coupling bothers me. What can we do to weaken the operational coupling? Well, as an architect, you might say, let's use REST instead of SQL. So let's wrap up that database, no longer allow direct access to its contents, but we'll provide an API. This is a very common kind of transformation for us to do these days. And if we do that, now our operational coupling is still kind of strong, but less so than before. The reason that it's less strong than before is because if a SQL database gets a momentary interruption, suppose it gets restarted, as a client, I have to reconnect. Right? The SQL connection I had before is no longer any good. I have to make a new one. Now, if it's REST, I'm no longer keeping a connection open. I'm connecting long enough to get a result back, and then on my next request, I just connect again. So I'm a little more resilient to those momentary operational interruptions. Development coupling also weakened a bit. Now, if the database schema changes, I have a point of indirection in the REST API. I can ask for that REST API to insulate me from the schema changes and provide some version compatibility forward and backward. The semantic coupling is still strong, but it's all different. So instead of representing entities like table and column, well, now I need to know about the REST resources and whatever classes and entities I have on the consuming side here. So I still have to have kind of a one-to-one mapping from one side of that interface to the other. And the functional coupling is still pretty weak. So we can see that along these different dimensions, changing the style of the interface has weakened some kinds of coupling, but not all of them. And there's still many situations where I might have to make correlated change on both ends of this component. So let's go even further. Instead of REST, where the data provider has to be there, what if we go into a publishing mode and we invert the flow of control into something like this, where now we're publishing, we have a message broker, and we have a receiver that's receiving these things. Now our operational coupling is quite weak. The reference data system can continue publishing while the receiver is offline. The broker will accumulate the messages. The receiver will get them when it comes back up. Likewise, the receiver no longer has any runtime dependency on the reference data system. So we have successfully removed that operational coupling. The development coupling now is quite weak. We have multiple places where we could intercept changes. So the broker could do some message mapping if we want to isolate changes on different sides. Be careful about going too far with mapping in the middle, or you end up recreating the dreaded enterprise spaghetti box, and we kind of got away from the ESB era a while ago. But we do have multiple places where we can isolate ourselves. And then in terms of semantics, there's still strong semantic coupling. After all, we are looking up reference data. We need to know something about what that reference data means. So we can't really completely get away from semantic coupling. What's interesting is the functional coupling has now increased. For those of you in the back, the bottom line says functional coupling is now moderate. All components must share the same messaging technology. And so now we're exposed to versioning concerns about the messaging technology itself. We have successfully weakened the operational coupling at the expense of increasing the functional coupling. We've also introduced some extra running components, so we've kind of increased the complexity of the operational landscape. Now, my point in showing you these is not to claim we should go all in one direction or all in the other direction, but it's to say, as we make these changes, we are certainly trading some things off. Where is the proper place to land on that trade-off? You have to decide that. I can't tell you as a general rule which way we should go. You need to decide, can I live with the operational coupling? Can I live with the functional coupling? How much semantic coupling am I okay with? The other thing to note is that through all of those transforms, coupling was still present in different kinds, but it's necessary. Again, if they were completely uncoupled, they wouldn't talk to each other, they wouldn't do anything. Now, I will say, my primary motivation these days is not about the operational coupling, because I'm not in ops anymore. My primary concern is around the semantic and the development coupling, because I find that those inhibit our ability to change functionality more than the operational coupling does. The operational coupling we can deal with by providing versioned APIs, by using shock absorbers, circuit breakers, governors, bulkheads, and so on, so that we can roll out changes effectively into production. But the development and the semantic coupling will stop you from making the changes in the first place, and especially the semantic coupling. I want to explore that semantic coupling just a little bit more, because it's not as obvious. You can't always grep for this or do a find in files to see where it is. So I have here an example from a retailer that I've worked with. And this is not an uncommon kind of enterprise architecture for a retailer. We have items being defined far upstream in a system called Retech, which is like retailing technology. Those were being published into an IBM product information management system. Those were getting passed through Informatica, which is like this data transformation and mapping tool, and then published downstream to a whole bunch of places. I was down here in this .com arena. Now, throughout this entire enterprise was this notion of an SKU, or stock keeping unit, often pronounced SKU. The original notion of an SKU was just a number. It was literally a number that you could use to go and see how many pieces of inventory do I have. But over time, people found it useful to attach other ideas to this number. So display attributes, dimensions for things that get stocked on a shelf, weight for things that get moved around by truck or train, price, costs, and so on. People kind of forgot that the SKU was meant to be just an identifier, and they started to think that an SKU actually was all of these things. You would say, what is an SKU? And they would say, well, it's your price and name and cost and dimensions and weight and so on. Well, no, not really. Those are all attributes of the thing. But this notion of the SKU had leaked out and become pervasive throughout the retailer's systems. One day, well, it wasn't all of a sudden, but I'll tell it as if it were all of a sudden. One day, they discovered that they needed to be able to change prices on a great many things all at once. This happened to coincide with selling digital items like audio tracks and skins and hats and so on. But the systems they had up front wanted you to enter a price manually for every SKU. They said, well, we can't do that because there's now 22 million items. And if we want to change the price on all of our 128 kilobyte or kilobit bitrate songs, we can't go manually update 12 million items. So they invented a new notion called the price point. And they attached that up here in the product information management system and said, a lot of these items are going to be related to a price point, and if I change the price point, then that affects the price on all of these items. Perfectly reasonable change. After all, every problem in computer science can be solved by adding a level of indirection, right? The difficulty came when they made a fateful decision. It wasn't fatal, they're still around. They made a fateful decision to publish the price point table everywhere. Now, what this meant was that every data feed through the whole rest of the enterprise now had to accommodate a new table. You had to make that change in all of the databases for all of these things, and everyone had to implement the logic to say, does this item relate to a price point? If so, use that price. If not, use the price that's in the item itself. I call this a semantic leakage. You see, the price point idea was invented to solve a problem in the product information management system. That problem didn't exist anywhere else. The problem was all about leverage in changing the prices. Nobody else needed to change prices. Nobody else was even allowed to change prices. So what I would prefer to have seen was that that concept of price point would have gotten flattened into the data feed. And then for the rest of the systems, it's just that a SKU has a price. And how and where that price originated and how it's updated should have been hidden from everything else downstream. I call this kind of chain of semantics a semantic polymer, because it's like building a long chain hydrocarbon molecule. It becomes stretchy, it's hard to cut, it takes a lot of energy to move, and that price point decision ended up costing many millions of dollars in implementation for the downstream. So how can we get out of this? Well, I like to go back to David Parnas in a paper he wrote in 1972 on decomposing systems into modules. This was the paper that gave us the idea of information hiding. I'm going to go through it a little bit quickly, but he was talking about building a keyword index. This is what you did before you could do online searches so quickly. You would take a single sentence, and you would index it with each word in first position. You would then alphabetize all of those, and you'd make an index so that you could find the word. If we wanted to look for all the occurrences of software, we would go to S, we'd find software, and we'd find every sentence that included the word software, together with a reference back to the original text. In the paper, Parnas points out two different ways of decomposing this. So he's got this way, which is very typical, sort of a linear flow. Input builds an array, the circular shifter goes in and makes a new array with pairs of indexes. Alphabetizer makes a new array of pairs. There's a lot of mutation going on, but that's what you did when memory was expensive. This works. It's a viable structure for this application. One gets the sense in reading the paper that he wrote the paper to win an argument in print that he lost in the office, that his design was not used, and so he wrote this paper. The paper has long outlived the program. If we consider all of these kinds of changes we might want to make in that first structure, it turns out every change here requires a change to every module. Parnas presents a different decomposition, one that we would now recognize as being based around interfaces. So we have a module called line storage that offers an interface for setting and retrieving characters, changing words, and so on. We have input, which uses that interface. We have circular shifter, which provides that interface. We have the alphabetizer that uses the line storage and presents a new interface. And then we have output, which is basically just a for loop over the lines. I'm going through this pretty rapidly. I recommend reading the paper. It's a good one. Turns out in the second decomposition, each of these changes requires a change to only one module. And so both decompositions work at delivering the functionality, but one of them survives changes much better than the other one. Now, Parnas talked about this as the effect of hiding information. He later said he should have called it hiding decisions. So the decision about how to store the characters was encapsulated in one module and hidden from others. With the benefit of hindsight, I think that there's an additional factor that made the second decomposition survive better, and that has to do with the interfaces. When we look at his decomposition in kind of modern notation, we realize that there are a small number of interfaces being used and provided repeatedly. You see, in the first decomposition, every module had a unique interface. They were all calling each other. There really were not a lot of data types defined. And here, we have the line interface, and we have the ordered interface. And we can kind of plug them together this way. And so one of the things you can do to reduce the semantic coupling and improve your ability to change is actually reduce the number of interfaces you have and reduce the number of data types. Now, I'm not saying reduce the number of modules or the number of components, but I'm saying look for opportunities to reuse the same interface definition or the same data type definition in more places. There's another quote by Parnas, by the way, where he says it's better to have 100 functions that operate on a single data type than 10 functions each on 10 data types. Another way that we can look at reducing the coupling is in terms of orthogonality. So we have this notion of separation of concerns, which is usually about the development or the operational coupling, but I think we can also apply it to semantic coupling. I'm going to walk through a few examples here. This comes from Simon Brown's c4model.com. It's one of the example systems that he uses, and I like to use it as a way to illustrate how we can look for these coupling problems. That flickering is really getting irritating. So we have down here a component called an orchestrator. We have a risk calculator, and we have a report generator. So at a particular point in time, the orchestrator calls the risk calculator returns something here, which is then handed off to the report generator. And so, obviously, there is some interface. The risk calculator is producing values of some type that the report generator knows how to consume. So there is some possibility for semantic and development coupling there. We have several components over here that are importing data from various external systems. They probably have similar implementation needs. So they're all calling out to various databases. They're doing it periodically. They're getting back SQL results, and they're trying to manipulate it and show them to the orchestrator. And so there's likely to be some functional coupling among those components. Up here we have something interesting. We have a report checker that's supposed to see if the report was generated by the appropriate time of day. The report distributor is the piece that publishes it out onto a file system. The report checker seems to be missing a connection to the file system. And so it's not clear how it's detecting whether the job has been done. So there may be some latent coupling there and likely some functional coupling that will surprise us later on. And then the orchestrator itself, I mean, kind of the nature of orchestrators is that they sit in the middle and they're coupled to everything else. So it would be a clear place that I would look for that. A few things we could do. So if we're over here looking at our risk calculator and report generator inside of a single application, we might use a module to define the interface. If we were going across multiple systems, I might look for a media type that we would use for representing anything that can be reported on. So we might elevate the level of abstraction from something very concrete to a risk calculator into something more like, an n-dimensional hypercube or slice of a hypercube, and report generators would know how to visualize various pieces of that. Over here with these implementation details, we probably want a shared library to isolate that functional coupling into one place. Up here, when we've got the file system layout, we probably want some kind of a module to represent how the file system layout is done so that we could then extract that common behavior from the report distributor and the report checker. Now, I went through that kind of fast, but the key points that I want to have you think about is we solved some problems with coupling by introducing new modules. So in other words, we're looking at the components, the runtime structure, and we added things to the development time structure. In other places, we're going to be looking at the development time structure and solve it with a runtime solution. So the idea is to rotate your perspective and don't solve every problem in the same dimension where you're observing the problem. This applies with data and code as well, although if you're a Lisp programmer, then these two later statements sort of seem to be tautological. So in summary, when we're looking at coupling, Coupling determines the degrees of freedom you have in your system. Think about the knee swinging in one plane, but it also determines what's easy to change in my software system. It enables some movements and makes some movements easy, other movements are going to be difficult. And it can connect effects from far apart. Keep in mind these different kinds of coupling. So operational is the runtime coupling. Development is when do I have to deploy things together. Semantic is when do I have to change things together, even though they don't directly interact. Functional is the shared implementation. And then incidental is there's no damn good reason for it. So hide decisions where you can. Figure out which degrees of freedom matter. You'll have your change cases that let you decide that. Watch out for these semantic polymers. Use all the structures you have at your disposal. And in every case, prefer making the coupling explicit to having it be latent or tacit. That's what I have learned about uncoupling. Thank you for your time and your attention.